Okay, good morning, everyone, and welcome to our Improving Fire Sprinkler Safety with Backflow Prevention webinar. I'm your host, Greg Jackman, the Specification Program Specialist here at Watts. Today's webinar is the next installment in our series of webinars specifically designed for you guys, our engineers, architects, and specifier customers. Karen, can you move to the next slide?
Yep.
Just to give you a little bit of background on our webinar series, we hold several webinars throughout the year that cover a variety of topics. Our presenters and our panelists are always our in-house and technology and product experts. And thanks to our partnership with ASPE, we're able to provide you guys with the 0.1 CU credit if you stick around for the entire webinar. After today, our next one will be next week on October 22nd. It's entitled The Science Behind Sanitary Design, Food, Life Science, and Healthcare Facility Safety. So hopefully you already got an email invite on that, but if you haven't, I'll send a link to the registration page here in the chat window, and you can register if you like. Next slide. So with that being said, I'd like to introduce you to the presenter of today's webinar, Cameron Rappaport, our Backflow product specialist at Watts. Cameron works with engineers to provide support in managing our backflow prevention product line, including new product development training. Next slide. Quick housekeeping item before we get started. During the duration of today's presentation, all the phone lines are muted, but we encourage you to submit questions via the chat window. Just hover over the chat icon at the bottom right hand of your WebEx, and you can type in your question there. And then depending on timing and how fast we're moving throughout the presentation, we'll either address them during, but we'll definitely get to them afterwards. So with that said, let me pass it off to Cam to get started.
All right. Thanks, Greg. I got to give myself a black tie photo like you do in your little picture.
Very formal.
Oh, yeah, there's that red arrow.
Okay.
All right. So what are we going to talk about today? So improving fire sprinkler safety with backflow prevention. So that really works on two levels, right? One is ensuring that you're properly applying the backflow preventers and understanding how they operate for the safety of the actual sprinkler system, so to make sure the sprinkler system is working. But also equally important is we're using those backflow preventers to make sure that what is in the sprinkler system stays in the sprinkler system because it's not potable water. So really, we're using backflow preventers to protect our drinking water in general from hazards that exist within the sprinkler system. So we kind of have two levels there. So what we're going to try to do today is just understand why and where the backflow assemblies are used in the fire protection systems. We're going to talk about degree of hazard. So, high hazard versus low hazard, or health hazard versus non-health hazard, and how that can affect backflow selection, what the authority having jurisdiction is thinking about when they require one versus the other. Identify some key characteristics for backflow model selection in fire sprinkler applications. We're going to talk a little bit about type 1 and 2 detector assemblies. We're going to learn which approval agencies certify backflow preventers for use in fire sprinkler systems and kind of what each one means. And learn how flood detection systems are used in conjunction with a backflow. This is a lot to get through. I'm going to go pretty fast. Any one of these points, I could probably do an entire hour on. So it's going to be really an overview. If you have any other questions afterwards, right? Obviously, you can use them in the chat, or you can always contact me. We can take it offline, as they like to say. So I'm going to do a little terms and definitions, some basics of backflow at the beginning. This is for anybody who's not super familiar with backflow prevention or backflow preventers. I'm going to keep it pretty quick. So for those of you who are out there who are more experienced, this should just be a refresher. So just bear with me for a few minutes. So let's define some terms. Backflow, you hear cross-connection control a lot. So the division that might be certifying, regulating backflow preventers in a municipality might be the cross-connection control department. So what is a cross-connection? So it's defined by the EPA as any actual or potential connection between the public water supply and a source of contamination or pollution. So these are hazards to the building occupants and to the users of our potable water distribution system They can jeopardize the cleanliness and the potability of that public water system in the event of a backflow or back siphonage event. So we're here today because fire sprinklers are cross connections. The water in a fire sprinkler system is non-potable, and you have it connected oftentimes directly to a potable water source. So those components, including the piping, are not rated or suitable for drinking water. So you have a potable water source connected to a non-potable system that is a cross connection. They also, in that EPA definition, they mention actual and potential connection. An actual connection is a direct connection to a source of contamination. So in this particular image, right, this is just a home, it's not a fire sprinkler system, but you have your hydronic heating system. So you have a line directly connected to the boiler. The water in the hydronic heating system probably often has glycol in it, or it's just considered non-potable as a direct connection, an actual connection. A potential connection is something like a hose. So it's not necessarily connected to a source of contamination, but it could be at any time. And in fire sprinkler systems, we do have both actual and potential sources of contamination, which we'll get into. So backflow, right, what we're talking about, is the unwanted reverse flow of a liquid, gas, or other substance into a potable water distribution system. What I always tell people when I'm explaining backflow to them is that our water distribution system is built to operate in one direction. And when the direction reverses, you have a problem, especially when you have cross connections and contaminants downstream that are unprotected by backflow preventers. So in this case, a water main breaks. It has the potential to siphon any number of contaminants out of this building, out of the lawn sprinkler system. If you have dirty water in an unprotected sprayer submerged in a bath or a sink, something like that, stagnant water or glycol in the boiler, static water pools or fertilizer in the sprinkler system, that kind of stuff. So there's two kinds of backflow, or really two causes of backflow: that's back siphonage and back pressure. So back siphonage occurs when there is a negative or subatmospheric pressure in the distribution piping. Typically, there's something like a water main break or firefighting activity, something where you're actually drawing suction, you're drawing a negative pressure on the distribution system that's going to want to siphon things out. There is always the potential for back siphonage because you can always have a water main break. So if back siphonage is a pull from the supply side, you can get a push from the downstream side, which is back pressure. So it's when you just have a higher pressure downstream in that non-potable system than you do in upstream in the potable source. So in this case, thermal expansion, very common in fire sprinkler systems. So this one in particular example is a boiler, but you could easily replace it with a fire sprinkler. You fill it, the water coming out of the ground is often colder than the ambient temperature. Once you fill it, the water warms up, it expands, and it's going to want to force its way back into your drinking water. So you need a backflow prevention, and you need some means, in this case, of dealing with that thermal expansion. I actually have a great case here. This is backflow causing a restaurant to serve seawater, and this is actually a firefighting system. So customers in a restaurant near a waterfront complained of salty drinks. The contamination was eventually traced to an unprotected pump that was priming a line that serviced a high-pressure seawater firefighting system for the shipyard. So because the seawater system was kept at a higher pressure than the supply pressure, and the priming line was left open, it was actually pumping raw seawater into the drinking water line through back pressure backflow. So interestingly enough, a backflow preventer had been installed, but was removed and not replaced because it suffered some freeze-related damage. So this is a great demonstration of both back pressure, of backflow from a firefighting system, and the importance of protecting backflow preventers from freeze damage. So last couple of things in our kind of terms and definitions. Pressure, you guys are engineers, you probably don't need any explanation on that. I'm going to talk about both flow rate and flow velocity. So rate in gallons per minute, also is commonly in cubic feet per minute, especially when you're talking about water meters. And then velocity, the speed at which the fluid is moving. Here you have a flow curve, and it's really important to understand what is going on here. And we're using both flow rate and flow velocity. So the flow curve is simply the pressure loss across a backflow preventer. So this is going to allow you to design your systems knowing how much pressure you're going to lose across it. We'll often put a few different lines on here. So the first one is service flow. This is what we would call a kind of typical max flow for a system. And we peg it at 7.5 feet per second based on the nominal pipe size. So that's kind of your typical flow rate. We also have rated flow. So that's your ASSE defined rated flow. And for potable, like drinking water applications, a backflow preventer that's going to be supplying buildings, drinking water, your water fountains, your sinks, all that kind of stuff. We would typically use that rated flow as a maximum flow rate. But those systems, your drinking water versus your fire systems, have very different usage. And because of that, we have different max flow rates. You'll see a UL rated flow. So UL actually sets their own rated flows that have to get that the backflow preventers are tested to be UL rated. And that's going to be much higher. So for fire systems, we're going to use that. And the reason they're different is because one, fire systems tend to have much higher potential flow rates. And two, your drinking water systems, those backflow preventers are going to be used every day, right? It's going to be opening and closing. It's going to get a lot more wear and tear from that regular use. So you want to limit the max flow rate through that backflow preventer. For a fire system, it's got either going to be off or it's going to be flowing potentially a lot of water. So because the use case is different, we can use that different rated flow. The key elements of cross-connection control, this is true for both drinking water and fire protection system. We have our isolation protection, so that's point of use. So in a fire system, it might be the separation between a wet pipe and a dry pipe, or a wet pipe and a glycol system that's servicing outdoors. You also have containment, which is going to be right at the meter. So between those two, we get our total backflow protection. All right. So how do we choose which backflow preventer is appropriate for a given application? One really important factor is degree of hazard. So we have health hazard and non-health hazard. The non-health hazard or pollutants are any substance which can affect the color, taste, or odor of the potable water, but do not necessarily directly pose a threat to human health. So it could be an objectable odor, an objectable appearance, smells bad, it tastes bad, it looks bad, but not necessarily bad for you. A contaminant, which would result in a health hazard, is any substance which, if introduced to the potable drinking water system, will constitute a direct threat to life or health. So these are typically, chemicals. They could be caustics. It could be, raw water, some untreated water, which could potentially contain bacteria or some sort of disease. So this is going to be really important in backflow selection. So the big question is, what degree of hazard is my fire protection system? The best answer, of course, is to ask the authority having jurisdiction, which I'm just going to call the AHJ. This could be fire chief for the municipal water provider or an inspector, but at the end of the day, they have to sign off on the project and they get to decide. These are all typically local codes. But we do have some guidance and standard practices that I do see across the country. But again, this is by no means exhaustive, and you really have to refer to your AHJ. But your standard wet pipe system, no chemical additives, are typically going to be rated non-health hazard. So what can we do to a system that might make an AHJ designated a hazard? So one is we can add chemicals. So antifreeze, even though there's a lot of antifreeze glycols out there now that are not health hazards, right? They're not poisonous. Those are typically still going to want to upgrade that backflow preventer to a health hazard type backflow preventer. So if you have any outdoor loop in a part of the area, a part of the country where it's going to be exposed to freezing temperatures, and you fill that with glycol, that's probably going to get protected by a high hazard type backflow preventer. Also things like foaming agents, which you see in like aircraft hangars. Another big one is auxiliary water supplies. So these are actual or potential. So what I mean by that is, like you saw in that previous example, you're using seawater to fill a firefighting system. You could have an auxiliary water supply in the form of a reservoir, which, a pond, which is obviously non-potable, or even just a tank that's open to the air. So the type of tank could actually matter there. A potential connection could even just be a nearby reservoir, pond, body of water that the firefighters could potentially hook up to if they come with a pump truck. So even just a nearby auxiliary source could be enough for an AHJ to want that higher level of protection on the fire sprinkler system. The last one is they just might want it that way. Every once in a while, you see people just going from, in this case, double checks to RPZs, which we'll talk about, because they don't want to have to evaluate every system. They don't want to have to evaluate every time a system changes, every time a building permit gets built, they expand a fire protection system. They just want to say, we're going to call everything a high hazard, so we're always going to have that high level of protection. And that is their call. So always check with the AHJ, but these are the things that they're thinking about when they designate things one way or the other. Another thing I want to talk about is, what does NFPA say about backflow? So this is going to be your primary code organization for fire sprinkler systems. The answer is not a whole lot. They do say some stuff, so let's go through that. So under certain conditions, they want you to separate antifreeze and wet pipe systems with a backflow preventer, which we talked about, right? The antifreeze is going to be a high hazard, and you might be protecting that with a high hazard type backflow preventer, but the main system with a lower hazard one. Again, it depends on code. They say if you're using a backflow preventer, you're going to want to use an expansion tank or a relief valve. It depends on the size, the arrangement, or the type. But when you add that backflow preventer, you are isolating the downstream system, which means that you're going to want to make sure that when you do get thermal expansion, that pressure has somewhere to go. So expansion tank or relief valve, depending on exactly how big the system and what the setup is. There's a lot of guidance in NFPA 13 about that. You have to provide a means of forward flow testing. So just some way of making sure that that backflow preventer can be able to supply enough water. These shutoffs count as control valves, because that's what they are. So you don't need to necessarily double up on control valves if it says you need a backflow preventer and you need, say, an OS and Y. If the backflow preventer has an OS and Y, NFPA is cool with you calling that the control valve. They count as check valves because they're check valves. They must be accounted for in hydraulic calculations. So this is a big one, right? We talked about that pressure loss curve before. You need to make sure you account for that, because often the backflow preventer is going to be the thing with the largest pressure loss in the entire system. So you really have to account for it. And that is especially true if you're reevaluating systems that are being changed, or if you're changing out backflow preventers. Right? Retroactive installations require revised hydraulic calculations. If you're removing a backflow preventer and you're installing a backflow preventer that is not the exact same make and model, you really have to revise those hydraulic calculations. You could go from being okay to being in trouble with a higher pressure loss, especially if you're switching backflow preventer types. Right, using an RPZ to separate salt water and potable water, exactly like that example we had. You want to use an RPZ with non-potable auxiliary supplies or with antifreeze. Again, we talked about that if you have, some sort of reservoir you're drawing from or a non-potable tank. They do have some guidance on installation in pits. They say it must be accessible. Please make it accessible, right? People have to come in, they have to repair these, they have to get annually tested in most cases. So you're going to make it a real issue for your customer if testers can't easily access it. Of course, they must be listed for fire service, right? Got to have, that typically UL or FM. But at the end of the day, the national codes are the national codes, but it's up to local enforcement for them to tell you exactly how they want things done. So backflow preventers are highly regulated because that they are safety devices. So there's a litany of different standards and organizations that might list the backflow preventers or provide standards that they should be built to. I'm just going to go over a few that are the ones that you most commonly see called out when you're installing them in a fire sprinkler system. First is ASSE. It is the American Society of Sanitary Engineering. It's one of the main governing bodies. You'll notice that different backflow preventers will have different ASSE standard numbers associated with them. And between them and the other big certifying body, which is the University of Southern California Foundation for Cross-Connection Control and Hydraulic Research, I'll just call them USC, they're really setting the standards for the functionality of the backflow preventer. So making sure that the backflow preventers are going to do their job preventing backflow. So you also have UL and FM. So UL and FM are going to be the ones that certify specifically for fire sprinkler systems. Their requirements are a little bit different. They don't go so much into making sure the backflow preventer is going to work as a backflow preventer, but making sure that it's going to be safe to install in the system as far as, pressures and flows and a couple other things, which I'm going to get into. I also want to mention NSF. I see more and more lead-free valves going into fire sprinkler applications. And typically when you call for lead-free, NSF is going to be the organization that's going to certify that valve for being lead-free and for being appropriate for drinking water applications. So why would you need that? Well, you're separating a drinking water system from a non-potable system, but that drinking water is in contact with that valve. So some inspectors are going to want to see that be appropriate for drinking water. So you can see there's several more. Before I go in, I guess I'm just interested. So I had Greg create a poll.
Yes, thank you, Cameron. So our first poll of the day here, you can answer on the right of the WebEx. It's, do you specify lead-free fire sprinkler backflows? All the time, none of the time, some of the time.
Yeah, so I think it'll be interesting for everybody to see what's going on across the country. So at least we'll get a fun little smattering of different places across the country of all the people here on this webinar.
Yeah, leave the poll open for a few more seconds.
I'm just gonna close my blinds because I'm getting a lot of light in. It's getting some weird.
Nice day out. And we're all in here on a webinar. All right, I'm closing the poll, and you'll be able to see the results in a second. Okay, the results are up.
All right, so it's pretty distributed. We have about equal saying all of the time and none of the time, and a few less people saying just some of the time. So this used to be none of the time, and not that long ago. So it's really something that's coming out more and more. I know that there's several backflow preventers that we make for fire sprinkler applications that are just lead-free as a standard. So thank you for answering those poll questions. For those of you who did, that is interesting. So for those of you who are not seeing it, I would start thinking about it, because it could easily become a requirement in your area of the country.
Cameron, we do have one question that came through here. May want to address it now. What condition would cause thermal expansion in a fire system?
So it's just if the water is going to heat up, right? So especially if it's not like a hydronic system where you're actively heating the water, but I know at least up here in New England, where I'm sitting in Massachusetts, our groundwater, the water coming out of the tap, is always reasonably cold because our pipes are buried pretty deep. So if you have cold water coming up and that fire sprinkler is in a heated building, that water is going to warm up and it's going to get some thermal expansion. Or even in a glycol system, you put glycol in that system and you're going to get the swings from, if in the middle of the winter it's 0 degrees out and that system's full, and then in the summer it's 100 degrees out, you're going to get some thermal expansion, right? If it contracts at all, it's going to get refilled, and then once it warms back up and it wants to expand, it needs somewhere to go. So you get some thermal expansion in fire sprinkler systems, and NFPA does specify how you want to deal with that, whether it's an expansion tank or a pressure relief valve. That's a good question. All right. So one thing I do want to go over really quickly is when people ask, you get all the time, especially for things like double checks. Why do I have to install this thing instead of just 2 check valves, right? Backflow preventers are, they're more expensive. And people just don't understand the difference between just 2 check valves and a double check backflow preventer assembly. And the answer is backflow preventers are much more heavily regulated, right? You can release a check valve onto the market, not necessarily a UL rated check valve, but with far less testing, far less oversight over its operation. So I'm just going to go through a little bit of what ASSE and USC require, which separates backflow preventers from just check valves. So what are they testing? They have a maximum pressure loss at rated flow. So the backflow preventers have to be able to close up tight, but you can't lose too much pressure through them, and that's by size and by type. They have a minimum of 150 PSI working pressure, 175 PSI for fire. So you'll see almost all of them rated to 175 PSI. You have a temperature range that it has to meet, right? So from right above freezing all the way up to 140 degrees. For reduced pressure principle or reduced pressure zone type backflow preventers, right? The RV cannot be easily connected to pipe or tubing. That's always a fun one. It makes it so that you cannot easily block off a backflow preventer's relief valve, which is why air gaps are specifically matched to individual backflow preventer models. They have to be inline serviceable. They have to have removable seats, and they have to be serviceable without any special tools. Test cock size is dictated. You do have to do a hydrostatic test to 2 times that working pressure. So it's going to be tested with all the components inside to at least 350 PSI. That also includes back pressure testing. So those individual check valves will have 350 PSI back pressure applied to them, and they have to stand up to that. They have to work afterwards, and they have to not leak. They also check that check tightness at extremes of temperature and pressure. So they're going to be running it at 40 degrees. They're going to be running at ambient temperature. They're going to be running it at 140 degrees. I think they do 100 hours at 140 degrees, and then they retest the checks to make sure that they haven't degraded it all. They're going to do it down at, I think they go down to 40 or 50 psi. It's got to work. They'll work it at, and then they go all the way up to 175 psi. So there's a lot of testing at the extremes of those working temperatures and pressures. There's a minimum amount of our relief valve discharge, which we'll talk a little bit about. There's back siphonage testing. There's cycle testing, so it's going to cycle the valve. It's 1,250 cycles of 4 different tests, so it's going to go through 5,000 cycles of different rates of flow, getting back pressure, getting back siphonage, flowing again. They're going to subject the body to a 4 times pressure test, so 700 psi. And it can't leak, it can't deform. They've also incorporated some of the UL stuff, so a seat adhesion test, that's to make sure that when these valves are closed for a very long time and they want to open back up again, that they will. We're going to do high velocity testing, so they're going to run water at 30 feet per second through it, make sure that still works afterwards. And of course, there's a 1-year field test. So there's a lot that goes into certifying a backflow preventer for use. And this is just not even necessarily for fire use. This is just certifying a standard type of backflow preventer. So ASSE and USC, like I said before, are really concerned with making sure the backflow preventers prevent backflow. UL and FM, what do they add to the table? So they have some of the same requirements, but in addition to what ASSE and USC require, they have some more material standards, so material sizes, connections, corrosion resistance, clearances. So they're a little bit more concerned with the makeup of the valve, so making sure it's being made from high-grade material. No special tools required for servicing. They do a 50,000 cycle test for the springs. They're just going to open and close that flapper or that check 50,000 times to make sure that it's not going to break after all of that. They do that seat adhesion test that ASSE also now requires. They do a high velocity test, so they're going to be at 25 feet per second for an hour. And they do have a maximum pressure loss at 15 feet per second. FM, they do some of the UL stuff. An interesting thing is that it only applies to valve sizes 2 inches and up. So if it's below 2 inches, FM doesn't have a standard for it. They also care about clearances. So those are all the standards, right? So these are all the things that make a backflow preventer suitable for a fire protection application, and it's a lot, right? So that's why these are more than just check valves. So I'm going to talk about the different kinds of backflow preventers, some considerations when you're specifying them. First one I want to talk about is dual checks. I'm seeing more and more dual checks because I'm seeing more and more residential fire sprinkler systems. So these are non-testable backflow preventers, right? They don't have test cocks. They're typically not required to be annually tested like a testable backflow preventer is, a double check versus a dual check. They're for non-health hazard, but they are rated for back siphonage and back pressure and continuous pressure. There are UL listed, this ASSE 1024 dual checks. Like I said, typically these are going into residential fire sprinkler systems. Residential fire sprinkler systems are not, they're getting more common, but the kind of standards behind them and how those are going to be interpreted and enforced have not really been fleshed out as much. So on a residential system, you might see a requirement for a dual check, which case you would want to use that UL dual check, that ASSE 1024 device. They might want a testable backflow preventer. They might want a double check valve, but they might not require one at all. If you have something like a passive purge, so in these residential systems, you see sometimes that you'll just run it to a toilet or something like that, where you're going to get some flow through the system. And as long as all the components are certified for potable water use, they might not even require a backflow preventer. But I didn't want to bring up those dual check valves because we're seeing them more. I also want to talk about single check valves. Single check valves are not backflow preventers, but they were very, very common in fire sprinkler systems before they were required to put backflow preventers on there. So you do see these. They are grandfathered in. Sometimes when you replace them, you can replace with another single check. Or sometimes when you replace them, you have to upgrade to an actual backflow preventer, a double check, or an RPZ. But like I said, you do see them. They're very straightforward. It's a single check valve. They aren't as highly regulated, but they still do have to go through all of those UL tests. The 50,000 cycles, making sure the materials are appropriate, doing seed adhesion tests, that kind of stuff. So double check valve assemblies. These are ASSE 1015 devices, and I will say these are still the most common that I see going into fire sprinkler applications. They are for non-health hazard. So it is a lower level of protection, but like I said, in your typical wet pipe fire systems, these are still going to be the most often installed and specified. So you do have to allow space for testing and repair. Please allow space for testing and repair. I know that mechanical rooms are getting tighter. They want you to fit more things into a smaller space, but you really need space around that backflow preventer because someone is going to be in there, or very likely that someone's going to be in there testing it every year. These can be installed in a vault. They can be installed below ground, which you can't do with an RPZ. They can also be installed vertically. So you do see those, but typical use, chemical-free systems, no auxiliary water source. Right, these are pretty simple. There are 2 checks, 4 test cocks, 2 shutoff valves. Right, the shutoff valves are important for isolation for testing, and the test cocks are used to test it. The individual checks have a minimum of 1 psi pressure loss across them. So as soon as the differential across that check goes to 1 psi, it should be shut and be drip tight. And that is what they are testing for when they go and test these valves. Usually they'll be more than 1 psi. They'll be between 1.5 and 3, depending on the model. But at the very least, they have to be 1. That 1 psi doesn't matter how big, right? This is like a 1-inch device. It looks like some, yeah. This is more like a 8 or a 10-inch device. They work exactly the same way. The standard is exactly the same, although the smaller devices, they allow a little bit more pressure loss across them, but it's still 2 1 psi checks. So that's your low hazard device. What is your high hazard device? And it's a reduced pressure zone assembly. You hear them called RPs or RPZs. These are ASSE 1013 devices. And there you're going to use for those health hazard applications when you have added chemicals, when you have those non-potable auxiliary water supplies, or just when the AHJ requires it. The big things here you want to look out for is they have different installation requirements. They cannot be installed vertically. So especially if you're replacing an existing double check that's installed vertically and you have to replace it with an RPZ, you're going to have to do some repiping. They also have to be installed 12 inches above grade. That is so that the relief valve, when it vents that water has somewhere to go, right? If it's down in a vault and the relief valve opens, it's going to fill that vault up, and then you have a cross connection at the relief valve because it's sitting in non-potable water. So those are the 2 biggest considerations. You also have to know that water will occasionally or can occasionally discharge out of that relief valve. And it can be quite a bit of water. So making sure that your customer knows that, the contractor knows that, and that you put it in a place where that will be prepared for the potential for that water discharge is very, very important. Another poll question. So have you specified an RPZ or an RPDA, which I'll get to, in a fire, which is the reduced pressure zone detector assembly in a fire sprinkler application?
Yep, polls open on the right. A lot of you are figuring that out. Pretty easy.
Yep.
Leave it open for a few more seconds here.
I think I did see a question come in, which is that weren't RPZs, didn't they used to be able to be installed vertically? Yes. Right now, the only RPZs that I know of that USC has listed to be installed vertically are the 3/4 and 1-inch Watts LF909, which you're not really going to see on fire protection systems. So right now, there really is no fire protection RPZ rated for installation in that vertical orientation. So just USC over the years has tightened up their regulations. USC Edition 4 was, a third of the size of USC Edition 10. So really no longer can you install an RPZ in the vertical up whatsoever outside of those two models, right? Or that one model in two sizes, that 3/4 and 1-inch LF909.
Okay, Cam, I ended the poll and the results are up. They're up right now.
Okay. So yeah, the majority of people still not specified in RPZ. Like I said, the majority of applications are double checks or double check detectors. So about 2/3 of the I got that wrong. About 2/3 of the applicants have specified an RPZ. It's my bad. And about 1/3 have not. So there's still parts of the country where if you're just doing a lot of standard wet pipe systems, you're not going to see that. So it's interesting. So you still have a lot of, 1/3 of the respondents still have never seen or specified an RPZ in a fire sprinkler application. All right. We'll move along. I got to go fast because I'm running out of time. We got a lot to cover. So RPZs, how do they work? It's still 2 check valves, but the big difference here is that you have a 5-pound first check instead of a 1 pound. So when you're testing this, you need a minimum of a 5 psi differential when that seals up, and you have a differential pressure relief valve. So when you hear relief valve, you often think people think that this is just going to relieve excessive pressure. That is not what these do. These are differential pressure. What it's looking for is it's looking for that pressure across the first check. So here you see that supply pressure, the inlet pressure, is pushing on a diaphragm. That diaphragm is going to shut the relief valve. And then acting on the other side of that diaphragm are 2 forces. You have the pressure between the 2 checks. This is the reduced pressure zone of the reduced pressure zone type backflow preventer. And you have a spring that is equivalent to 2 psi. So what that means is when this backflow preventer is healthy, that should always be closed because you should have a 5-pound differential plus, minus the 2 psi equivalent of the spring. You have 3 psi holding that shut. This relief valve will open when the pressure in that middle chamber gets within 2 psi of the inlet pressure. It's not always exactly 2 psi, but the 2 psi is a minimum. What that means is if you get debris in that first check, it will want to equalize the pressure across that check valve, and the relief valve will open, and it will potentially stay open. So there's that math, right? 5-pound check. Second check still a 1-pound check. That 2 psi spring, right? Should be holding everything closed. I want to say one more thing about this before I move on. What that 5-pound check means is that these have a higher pressure loss through the valve. Often, at least 5 psi more, sometimes more like 7 or 8 psi more, depending exactly on the model. I was saying flow arrows would be helpful. Yeah, we're flowing from left to right across here. Sorry. Because you have a higher pressure loss, if you're replacing a double check with an RPZ, you really have to redo those hydraulic calculations. So that's something that's really important. And keep that in mind. If you're not doing a lot of RPZs, you're going to have more pressure loss through these than you would typically experience with your double checks. All right, let's talk a little bit about metered detector assemblies. So fire sprinkler systems are typically unmetered, right? They're for a few reasons. One, there shouldn't be any usage, so why would you meter them? Two, we don't want to discourage people from having their fire sprinklers go off if there's a fire. So, we've kind of all decided that if someone's building is on fire, we're okay with the water being used to put out that fire being free. And two, it would be really expensive. Fire lines are often a lot bigger than the drinking water line, and 8-inch, 10-inch fire meters, they do get made, and they're really, really pricey. But the municipalities, they want to keep track of that non-revenue water, that water that they know is getting used or lost somewhere in the system, but people aren't paying for. So they want some way of seeing if that's happening in a fire sprinkler system. What they use are detector assemblies. Originally, the first thought was, well, we'll just put a bypass around the backflow preventer with a meter. That meter will register any flow. It's not going to get all of the flow necessarily, but that is a cross connection, right? So because it's a cross connection, it also needs to be protected from backflow preventers, from backflow. So we have detector assembly type backflow preventers. So first one is a double check detector assembly. It doesn't say at the top. Okay, yeah, there's a double check detector assembly, or DCDA, ASSE 1048. And the big thing here is there is a bypass. So it's pretty clear on this, little 2-inch guy up at the top. You're after the first shutoff and before the second shutoff, you are going into that bypass. You're running through a meter. You're going through another backflow preventer, right? Because if you're bypassing a double check, there has to be a double check in the bypass. It is very important that whatever you're bypassing has the same, there's the same level of protection in the bypass. So if you're bypassing an entire double check, you need a double check in the bypass. If you're bypassing an RPZ, you need an RPZ in the bypass. If you're bypassing a single check, something like a type 2, which we'll talk about, you need a single check in the bypass. So these are monitoring unauthorized water usage. It could be a leak, or it could be someone stealing water because they know that the water is free, or it could be just they tapped into a fire protection system, they didn't realize it, and they're inadvertently stealing water. The regulation behind this is that the first 2 gallons a minute have to go through the bypass. So that's what they're testing, or one of the things that they're testing when they do that ASSE 1048 certification. So what that means is that you're not necessarily going to get all of the flow, or whatever that leakage, that unauthorized water usage, not necessarily all of it is going to go through that meter, but some of it will. And if the meter is going up and the building wasn't, you didn't test the fire system and the building hasn't been on fire, there's some usage downstream that shouldn't be happening. I'm probably going to skip this because I'm really running out of time. But the big takeaway is that, right, if you're bypassing 2 checks, you got 2 checks in the bypass. So it's a double check and a double check. And the first 2 gallons a minute go through the bypass. And we do that just by biasing the checks. So making sure that these checks are a little stronger hydraulically than the checks in the bypass. So that's going to bias the first few gallons a minute through that bypass before the main valve opens up. And of course, you get more flow, the main valve opens up, you're going to get most of your water through that. So what is the type 2? So type 2 bypasses only the second check. So there's only a single check in the bypass. So why are we doing this? But first of all, I would like to know if people have heard of it. So we're going to open up another poll.
Poll's open.
Yep. So what is your experience? Have you never heard of a type 2 detector? Have you heard of them but never actually specified or installed one? Or have you never specified or installed one? So while you guys are answering, I'm going to get a little ahead of myself. Why are these being used? And this was really an ask from the fire protection community. They wanted a way to figure out how to make backflow preventers less expensive and have lower head loss. You actually get lower head loss through type 2 detectors. It basically has to do with tolerance stack-ups. I have a whole other presentation on that if you want to learn more. So Greg.
Okay. Closing the poll now. I'll pop up the results in a minute.
All right, almost half have never heard of them. What, like 10 or 15% have actually specified or installed them. Maybe even have specified or installed them, but not necessarily known it was a type 2 detector. So I'm glad we're talking about them. So, right, there's the why, right? So we're responding directly to the fire protection industry's request. There was an ASSE work group 21 years ago, and they wanted to address the cost, size, ease of installation, pressure drop, and reliability after long static periods of these backflow protectors. There's actually a fun article from Rand Ackroyd in my hometown from Newburyport, Massachusetts. And what the Type 2s really address is the cost and the pressure drop. So you'll notice in these two, we have an RPZ and an RPDA. And you actually have a higher pressure loss to the RPDA. And that is because you have to strengthen those checks in the main valve to ensure that the first 2 gallons a minute go through the bypass. There it is. This is reflected in the standards. If you look at the ASSE allowable pressure loss, you get 2 more PSI allowable in a DCDA than a DCA and 4 PSI more in an RPDA versus an RP. Fire protection engineers and fire protection contractors do not like that, right? They want as little pressure loss as possible while still maintaining the protection of the backflow preventer. So you actually get a little less pressure loss using a type 2 detector, especially in RPDAs. So are they safe, right? Are they protecting backflow? And they are. So I like to think of it as, we have direction of flow, left to right. I like to think of it as 2 different backflow preventers. So you have your main backflow preventer, right? 2 checks, 4 test cocks, 2 shutoffs. And then I like to think of the bypass as part of a backflow preventer that just sizes down to a 3/4 inch after the first check, right? So you still have 1 check and then a second check protecting the flow through the bypass. So you're only bypassing 1 check, so you only need a single check in the bypass. This allows it to have cheaper bypass assemblies, and it does allow for a little less pressure loss because you only have to deal with 1 check being biased a little stronger. Like I said, there's some tolerance stack of stuff in there that allows you to take some off. In the wild, right, they'll look something like this. After the first check, you'll have the bypass come off. It'll go through your water meter, a single check, and then it'll come back in after the second check. So your first 2 gallons a minute, go, I think I have a red line. Yep. That first check on the main valve will open and then it'll go through the bypass. That second check will be closed. That's how the meter gets that registered. And then, fire flow, you're going to open both checks. If you have a fouled first check, you still have a single check protecting it, just like you would in a standard double check backflow preventer. We also have type 2 RPDAs. Same considerations as standard RPs or standard RPDAs. So your type 1, right? You need a full RP in that bypass. So here you see your main valve, you see the RP in the bypass because it's bypassing both checks and the relief valve. And this type 2 assembly, it's a type 2 at the top in the middle. You'll see that it's coming off after the first check. There's a single check in the bypass, and it's coming in after the second check. So again, here's your standard type 1. You're bypassing 2 checks in a relief valve, so you have 2 checks in a relief valve in the bypass. On the first 2 gallons, and they have to go through the bypass. So RPDA2s, are they still safe? And they are, and this is why they've been part of the ASSE and USC listings for almost a decade now, actually. So your static flow, if it is fouled, right, the relief valve is going to go off because that relief valve is still part of that bypass assembly. If you think about it as you go from the first check, you go into that reduced pressure zone with the relief valve, then you go through that second check, that single check in the bypass, then it comes in after the main second check in the check valve. So that relief valve is protecting both the bypass and the main assembly. So this is really where you get a big difference going from a type 1 to a type 2, because you don't need a relief valve in the bypass. It's 2 less things to foul. It's 2 less things to test when the testers come in, and it's one less thing that has to go into the bypass. So I really encourage you guys to take a look at these. They're pretty interesting, and they've been certified for use, like I said, for almost a decade. All right, I know we're coming up on an hour. I'm going to keep going. I think this is one of the most important things, but if you got to drop off, I understand. So key selection characteristics. The first one is flow curve. So how much pressure loss and at what flow rate? Not every flow curve is built equal, right? Some valves have more pressure loss than others, but most of the time, a valve will be better in some sections than other valves, and then worse in some sections than that same valve. So at your flow rate, your max flow rate, one valve might be better than the other, but not necessarily at that UL rated flow. I think there's some questions about getting CEUs if you have to go to a meeting.
Yeah, I'll address those. Cameron, keep going.
Okay. You have to take really special care when you're replacing a valve with a different type of model. Like I said, you have to redo those hydraulic calculations, especially if you're going from a DC to an RP, because you're going to get 5, 6, 7 potentially more PSI lost through that valve assembly. There's size and weight. It affects installation cost, right? You have a big cast iron or ductile iron backflow preventer versus the newer ones that are stainless steel. Especially in the larger sizes, it could be hundreds of pounds heavier than the cast or ductile iron could be hundreds of pounds heavier than the stainless steel. So it will affect the end cost to that customer because it can require more time and more labor, additional manpower to install that valve. I also know there's a lot of pressure to make mechanical rooms smaller. And in general, newer valves have just been getting shorter and lighter. So that's a really important consideration that can save your customers money when you're specifying those valves. I encourage you to look at your specs, because typically, you put something in a spec, I know you don't want to change it, right? It can be, a lot of work to deviate from what you've been doing, what's been working for you for a long time. Those backflow preventers, those old ones, are still often perfectly good, but you can really do a favor to your customers, to the contractors, by taking a look at some of these newer valves that are a lot shorter in length. Orientation, like I said, is it approved for vertical? You can go in and ASSE and USC both have pretty friendly websites. You can go in and check that even those double checks, are they approved for vertical? And remember that those RPZs are not. You can also use different orientations. We have what are called N pattern valves and Z pattern valves. So here's your vertical. N pattern valves go up, over, and down. These are really useful for outdoors. If you're putting these outdoors, this will help to really limit the footprint because you don't have to put additional elbows on either end of the valve. This is what I call a true N pattern. Then something on the right, you have kind of a standard valve with those elbows between the shutoff and the valve body, and that's going to save you some room. So using these outside will really help save some room. You can also use these if you're going, especially the Z pattern. If you're installing a valve, you have to install an RPZ. You don't have a lot of room, and typically you'd want to go, up out of the floor into the backflow preventer, then up into the rest of the riser system. These Z patterns can help you save some room. They can also help maybe with some repiping considerations if you're going from a vertical double check to an RPZ, because you at least still have, the inlet is vertical, the outlet is vertical, but you do have to shift over a little bit. So I'd recommend taking a look at those N patterns for outdoor installations and those potentially looking at those Z patterns for the indoor ones. Other big one, shutoffs. Right? They have to be rated for fire systems. So typically OSY, post indicator valves, or butterflies. You have a lot of different end connections that can suit the system or the contractor. It's flanged or it's grooved, or it's flanged by groove or grooved by flange. You do want to check for approval. Backflow preventers are approved with specific valves. So you can't just order the backflow preventer valve body and select your own shutoffs. They're approved together as an assembly. So a few other things. Pumps. I get a lot of questions about pumps. The main thing, do you put it before or after? It depends. The main thing I want to make sure you do not want to starve the suction of your pump with a backflow preventer. Because you're getting that pressure loss through the backflow preventer, you're going to have less of available net positive suction head for that pump. That might not matter if you have a lot of available pressure off the water main, but if you don't, it's an important consideration. And as always, you probably want at least 10 pipe lengths after that or 10 pipe diameters of length after that backflow preventer before you pump. I understand it's not always possible, but that is best practice. Yeah, making sure you're avoiding cavitation by making sure you have enough pressure supplying that pump. I like seeing soft starters on pumps. They're a lot cheaper than they used to be. That'll just keep you from slamming those check valves open, which can potentially damage the backflow preventer. If you can ramp that up a little bit more slowly, that'll help for the life and of that backflow preventer and its internal components. Strainers. I know they're not certified. You can't always use a strainer on a system. Sometimes they're not allowed by the AHJ, but where you can use a strainer, they will help because it's going to keep debris out of that backflow preventer. It's going to keep it from failing its tests, and that's going to keep your customers happy. So use where allowed. Real quick, so I'm going to just a couple more minutes. RPZs. Water will come out of that relief valve, whether it's something getting stuck in that check or just normal pressure fluctuations in the system. How would you deal with that water? The first is drains. Drains are almost always missized. If you have a 6-inch RPZ in a mechanical room and a 2-inch drain on the floor, and you get something big stuck in that first check, the amount of water that's going to come out of the relief valve will quickly overwhelm that drain. So we, just like every other backflow preventer manufacturer, publish our worst case scenario relief valve discharge rates. You'll want to take a look at those to get an idea for drain sizing. If you have more questions about this, we have another CEU webinar specifically on RPZs. I would encourage you to check out. The other thing is flood protection devices. So one more quick. tell you about those flood protection devices, which you're installing RPZs. It's a really important consideration. And we'll be done.
So here's our last poll, and we appreciate you guys staying on. I can see a lot of you are still on, so that's great. Then after this, we'll get to the your questions shortly. There are a lot of them coming in, so we'll do our best to address as many as we can.
Yeah, I don't have anything for a while, so we'll stay on as long as you want.
Yeah.
All right, so about half have heard of them, or about 3/4 have heard or specified them, about a quarter have never heard of them. So again, I have an entire webinar on RPZs and RPZ discharge and how to mitigate it and what these devices do. If you're interested, but when I'm talking about drains, right, the drains are almost chronically undersized. And it's because if you look at this 2.5-inch RPZ, if you have 75 pounds of available pressure, worst case scenario, you're going to have 320 gallons per minute coming out of that backflow preventer. I'm not a drain expert, but I asked some guys, so maybe not be right. That's going to require a 4-inch drain pipe. It's probably going to require a bigger drain just because of the net available area in that drain after the grate is in there. So how many mechanical rooms with a 2.5-inch RPZ have a 4-inch drain pipe and a 6-8-inch actual drain? Not very many. So this is a worst case scenario. This is with basically nothing in the way. A check is destroyed. Water is freely flowing out of the relief valve. But it does happen. It does give you an idea if you get something big stuck in that first check, what could potentially occur. So one, using a strainer at least keeps the big things out, right? If big rocks cause big leaks, small rocks cause small leaks. But one thing you can do is use these flood detection systems. So there is automatic shutdown available. I'm not going to talk about it here because you wouldn't use that in a fire protection system. But a couple different manufacturers, so but these are commercially available from competitors as well, have ways of monitoring discharge coming out of the RPZ. So in this case, it's a wet switch in the discharge line. So if this valve is discharging water, enough water for long enough, it wets those contacts. That's going to send an alert, and then you can hook it into a BMS system. You can get wireless notifications, text messages, emails, phone calls, that kind of stuff. The other one that you mainly see is something that actually monitors the relief valve stem position. So it'll actually detect when that relief valve is open by where that stem is as it moves back and forth with that diaphragm. These are a great option to have. Customers, even contractors, often do not realize just how much water can come out of these things. They're relatively inexpensive, especially compared to how expensive water damage is. These always seem to release in the middle of the night when no one's there. And it honestly does not take a lot of water to cause $1 million worth of damage in a commercial building. So I encourage you to check these out. Check out the Mitigating RPZ Discharge webinar we did. It's also an ASPCU webinar. If you have any questions, let me know. I'm going to stop talking because I'm 10 minutes over.
All right, thank you, Cameron. Yeah, quickly before we get to our questions here, I just wanted to mention 2 of our digital tools we have available for you guys. The first one is Selexit, which is our online configurator. I sent a link to Selexit in the chat window. So with this tool, you're able to generate precise and optimal system configurations. It's going to help you accelerate size and configuration and selection processes for mixing valve systems, ACVs, and snow melting systems. The other tool I wanted to quickly mention is called Spec Hub. Spec Hub is our project specification tool. Again, I sent a link to it in the chat box. So the biggest benefit of Spec Hub is its speed. It's going to allow you to quickly select and specify Watts products in accordance to your building requirements and codes. It's going to save you time researching Watts product data online because it already has all that information in the tool itself. You're going to save time writing specs, plumbing schedules, gathering BIM files. After you're done creating your project or spec, it's going to automatically generate customized docs for you to download and share with any of your colleagues. So the biggest takeaway there is for the tool is just that we think it's going to save you guys time, and we believe that it's just going to make your job easier. So I just wanted to mention those two tools, and then we can jump into the questions here. There are a lot of them, and again, I appreciate you guys sticking around. Okay, first one here.
Yeah, if you don't have time and you still have a question, right, my email's right there on the screen. Shoot me an email, and I'll get back to you.
Do you have any recommendations on a decent software app solution on backflow test report management?
I do. I like Syncta. SYNCTA. It's the one that Watts makes, it's affiliated with us. It is run independently because we want to make sure that there's no conflicts of interest. But Syncta is great, right? So if you're out there and you're testing a lot, having a digital solution is really important, because if you're doing it pencil and paper, one, it's really easy to get back to the office and look at something and say like, oh God, is that an 8 or a 9, or is that a 1 or a 7? And two, these digital solutions, so Syncta is not the only one, but digital solutions in general allow you to keep better track of the tests, submit them easier. They can even do things like generate reminders to your customers that they have a test coming up. You know what happens every year. You might as well send an email to your customer saying, hey, we did your test last year. We'd like the opportunity for you to use us again this year. So yeah, if you do a lot of testing, I would definitely check out your digital test management resources, and especially Syncta. We've gotten a lot of great feedback on it. It's a really terrific program.
If the building has an FDC, does it make the health hazard because it could be unsure if the water from the truck could be from a dry hydrant source?
That's a great question. So I know in general the existence of an FDC will not make it high hazard. And again, I'm not your local code official, but it depends on the surroundings. So if you have an FDC and there's a pond right next to it, that might make your local code official want to upgrade that to a high hazard because of the potential of a pump truck hooking up to that. Or yeah, if there's a well or some other non-potable source right nearby. So it does depend on the surroundings, and again, depends on local code. But just the mere existence of an FDC will typically not make it a high hazard. I know that I think there's regulations now around the water that gets put into the trucks themselves. If you have a tank truck, making sure that that's potable. Usually after an FDC, you'll have a single check. You don't need another backflow preventer at that connection. Yeah, so I guess it depends on the surroundings, but just like your typical FDC will not necessarily require that higher level of protection.
Okay. Are dry valves and alarm valves considered to be backflow preventers?
They are not. So yeah, those alarm checks, or yeah, the check separating from a dry system, are not backflow preventers. They're just single checks. So you need something with, that ASSE, typically 1013, 1015, 1047, or 1048 stamp, and it'll be right on it, right? So ASSE requires the actual marking on the valve, but no, your standard alarm check is not a backflow.
Isn't there a concern of an RP going into a full RV port dump? What if a fire breaking out during this condition?
Yeah, that's a great question, and it is an interesting consideration. I will say code officials those are the people, between NFPA and your IPCs and UPCs and stuff like that. They have made the decision to balance those two things and require RPZs in these higher hazard systems. So one, I would say if an RPZ goes into full dump, it's probably going to get fixed pretty quickly because you're going to notice. The other thing is if you have a full fire flow through an RPZ, often that will shut the relief valve. So you'll actually establish pressure differential across the first check via flow. So if you have anything other than a giant rock stuck in that first check, it'll likely close up the relief valve once you get a reasonable amount of flow anyway. So between those two things, so yeah, one, just code officials having made the decision on that trade-off, and it will probably happen pretty rarely, and two, the fact that, yeah, if you get a lot of flow, it in most cases would close up that relief valve.
Okay, and do the test ports on a DCVA when installed below grade represent a potential cross connection if subject to flooding?
Yeah, but only if you open them. It's a good question. I would, it represents a potential cross connection, but those valves are normally closed, right? So you have to go in and open that valve, which you would either have to do underwater, which right, you have to drain that pit before you test it anyway, or you'd have to leave it open, and you would notice because water would be shooting out of it. So it's a good question, and an interesting consideration. But the relief valve, because it's not manually operated on an RPZ, it can open because of pressure fluctuations, or even if you have a leaky first check and you haven't noticed, right? And there's a water main break. That relief valve is going to be open. And if it's submerged, it's going to be siphoning water from a pit that shouldn't be installed in back into the drinking water. So I would say that's the big difference there, is that, a manually operated valve that's normally closed and should only be open for testing versus something, a relief valve that's going to be opening and closing just based on hydraulic circumstances.
Okay, I've seen soft seat check valves added after the RPZ to reduce spitting of the relief. Is this a common practice?
Yeah, so if RPZs are spitting because of pressure fluctuations, upstream or downstream, a soft seated check valve is a great solution to that. So typically you see, if you're having supply pressure fluctuations and that's causing spitting, you want a soft seated check valve on the supply side. Downstream, it's a little less common. I would say if you're getting, consistent back pressure from something like thermal expansion, having a soft seated check valve can help with that. A water hammer, really the answer to that is a water hammer arrestor. But yeah, that soft seated check valve will help kind of protect that backflow preventer from, quote unquote, seeing those pressure fluctuations and spitting.
If you have a static pressure of 100 psi at no flow, after the backflow preventer, will you still have a pressure of 100 psi or about 88 psi with the BFP loss?
Yeah, so you have static pressure loss across the backflow preventer, whether it's a DC or an RP. And it's how much, depends on the model. So at minimum, right? So if you have a DC, you're going to see a 2 psi, and at minimum, you're going to see 6 psi from an RPZ, but it's probably going to be more like 6 for a double check, and 10 to 12 for an RPZ. If you look at your flow curves, where the flow curve starts, right? Because it's not starting at 0, it's starting up on that y-axis somewhere. That is going to be about your static pressure loss, and that's because these are positive pressure closing checks, right? They have springs forcing them closed, so close before those pressures equalize, which creates that static pressure differential. So yeah, you should expect a pressure to static pressure differential across the backflow preventer. If you don't have one, that could be a problem, right? It could mean that your checks are fouled, or you've somehow gotten back pressure.
Did DDCs always have a BFP on bypass?
The double detector, I assume we're talking about, did DDCs always have a BFP?
Did DDCs possessive always have a BFPs on bypass?
I'm not sure what that means. So your double detector checks should have a double check in the bypass if it is a type 1 bypass. I believe it's been that way since the existence of the ASSE 1048 standard. Type 2, it'll have a single check in the bypass, whether it's a double check detector or a reduced pressure detector assembly. And those reduced pressure detector assemblies, the type 1s, the kind of standard ones, are going to have an RPZ in the bypass.
And what is the testing procedure for type 2 valves? Is it the same as a standard BFP?
Yes. So it's the same second check test, right? So most of your testing organizations, so whichever organization you're using, whether you're using a USC test or an ASSE or an NEWWA or TRIO, they should have a written procedure for testing the type 2 bypass. I know in the USC, in the 10th edition, it's right there in the testing procedure. But it's just like doing a second check test for a standard valve.
Do you test the bypass in a type 2?
Yes. Yeah, you do. Like I said, there are testing procedures written out for them.
Okay. What's the process for, I already addressed that one there. When looking at the pressure flow curves, does this include the losses due to the valves and elbows, or do we need to include those in our hydraulic calculations?
That is for the entire assembly. So if you have an N or a Z pattern, it includes the elbows. Actually, let's see if I can, go way back. All the way. Is there a faster way to do this? Probably. So if I go all the way back to flow curve, just do that. That didn't work. So I'll just keep clicking. So if you look at your flow curves, you'll often have 3 different lines. And those lines will be, horizontal, vertical. There we go. Figured it out. Boom. All right. So here you have 3 slightly different lines, and it says NH and V. Should be set end pattern, horizontal and vertical. So this is for probably a double check. Usually N, it's the same for N or Z, even though you might have a little bit of, gravity head differential. It's not enough to really make a difference. So you'll have different lines. So yeah, we'll publish the different rates, and you should use the one corresponding to the valve that you're actually install, whether it's horizontal, vertical, end pattern, or Z pattern.
Okay, if you have to make a repair on a backflow prevention device, possibly at a gym, where do current circumstances there's nobody on site and there's a possibility of draining the fire system, what precautions should you take?
Oh, that might be a little bit. There's no one on site. There's a possibility of draining the fire system. I would talk to the local fire officials. Because if you have to make a repair and there's a potential that the fire system is going to be inoperable for a long period of time, they might want you to get a fire watch. Yeah, that one's a little above my pay grade. Because if you're just going in and testing, right, one, you usually have to alert someone anyway, because as soon as you close one of those valves, it's going to set off the alarm panel, because those valves are usually monitored. So you probably have to talk to either you or the building owner is going to talk to some fire official anyway. But if you have to make repairs, and those repairs might be extensive, and it might render the system inoperable for a long period of time, I would talk to your fire officials about how to handle that, or at least talk to the building owner. Because like I said, usually if your fire system doesn't work for an extended period of time, and at least if the building is you've got to get a fire watch. So yeah, I would do some research. I'd talk to your fire officials.
Okay, next question here. Didn't the EPA recently come out with the final lead-free rule clarifying that lead-free BFPs are not required?
I want to say yes. Sounds like a question I should definitely know the answer to. But again, at the end of the day, so yeah, I don't think it's required by the EPA. I know it's not in like IPC or UPC right now. But local officials have the authority to require it if they want. So again, most of the time, probably doesn't have to be lead free. But if a local official wants it to be, that's the way it is. And I'm just seeing more of it, every year.
Okay, and how much discharge is expected if the valve fails? How to size the plumbing drains properly for the valve failure?
Sure. So we publish these curves, right? So this is for one of our 2.5-inch RPCs. All the other manufacturers should be publishing their curves as well. So this will give you a worst case scenario. So the way these are actually generated is you take the second check out, you turn the backflow preventer around, and you pump water in the outlet. So that's going to hold the relief valve open. So this is a worst case scenario based on your supply pressure. So, right, like this one, I said at 75 PSI, you have 320 gallons per minute. There's a lot of drain sizing tools available to you. So we have one. I'm not our drains guy. But I'm sure that every major drain manufacturer, you'd be able to tell them I have this much water potentially coming out. What size drain do I need? And it depends on a bunch of things like, what's your acceptable water level and what the piping after the drain is doing, the size of that piping, that kind of stuff. I would say keep in mind that this is a worst case scenario. Best practice would be to size to this, but you also might have trouble convincing someone they need to install a drain that's big enough. And that's why I think that those the flood detection systems are really important, because it's going to be hard to convince someone, to put a 4-inch drain in a mechanical room, especially if it's something where it's not necessarily in the basement or on the ground floor, but it's up in the 13th story somewhere. But yeah, we publish these curves, and then you can talk to a drain manufacturer and use a variety of online tools that are available to help you size that drain.
Do you recommend RPZs to be installed 20 pipe diameters upstream of a fire pump suction in a single soft seat check valve 3 to 5 feet downstream of the RPZ and before the fire pump suction?
Yeah, I would. I mean, 20 pipe diameters is a lot. I always heard 10. I could be wrong. That has more to do with the recommendation from the pump manufacturer than it does the guy who's making the backflow preventer. But yeah, in general, you want a good length of pipe so that you have laminar flow going into the pump. That's going to keep your pump happy, right? It's going to help prevent things like cavitation. And then that soft-seated check valve, that's really going to help with things like water hammer. Like if you have your pump going and your pump ceases, you can get that rush of pressure backwards. And you'd really want to protect your backflow preventer from water hammer. So that's why you would use that soft-seated check valve. So that sounds to me like a good standard practice that you're using. Yeah, and then in general, upstream of the pump, the other thing you want to just make sure is that your all of your pressure losses, including the backflow preventer, are still going to provide the net positive suction head required for that pump at that required flow rate.
Okay, another question here. Backflow before or after a fire pump. The fire pump valves, etc., are not NSF. How is it acceptable to install backflow downstream of fire pumps and still meet code? Typically, backflow preventers are on the suction side to protect the city water mains.
It's usually not acceptable. So that's a great point. Yeah, if your pump and your are not NSF approved, then you have to put your backflow preventer upstream, right? Because you have non-potable components. You have to separate those from the rest of the system. So in general, I would say you're absolutely correct. Most of the time it's got to go upstream. But you do want to look at, you do want to make sure you're not starving your pump. You might run into some pretty tricky situations if you are. I'm not entirely sure how to handle those. You have to talk to a pump manufacturer as well.
All right, Cameron, that is all we got today. Thank you very much for the presentation, answering all the questions. Thank you to everyone who joined us today. Your CU credit will be mailed to you. If we didn't get to any of your questions, or if you have any other ones that come up regarding logistics or specifications, you can email me at gregory.jackman@wattswater.com if you have any questions on our digital tools, Selects, and Spec Hub. For more of the technical and topic-related backflow type questions, you can email Cameron at cameron.report@wattswater.com. And once this webinar ends, it's going to bring you to our hub page where you can learn more about our backflow solutions like Ames Derringer and Sentry Plus Alert. There's a video, flyer, brochure you can download. There's a link where you can request to be contacted by your local rep if you have any further questions to discuss a project or anything. The next few days, we will be posting a recording of this webinar and a short quiz on this hub page. So if any of your colleagues weren't able to attend today and they would still like to earn the 0.1 SBC credit, they can take that quiz and do so. You'll be receiving an email with a link to that hub page where the recording quiz will be as well the next few days. So that is all we got. Thank you all very much again for joining and sticking around. That's it. Have a great rest of your day.
Thanks so much, guys.